There is a faint patch of light in the northern sky that is easy to overlook. It has no sharp edge. It does not announce itself with the steady brightness of a planet or the clean point of a nearby star. Under a dark sky, it appears as a small pale stain among the constellations, as though someone had touched the night with a thumb and left the slightest trace behind. That trace is the Andromeda Galaxy. Its light has traveled for about 2.5 million years before reaching Earth, yet distance is only the first scale hidden inside it. The stranger scale is the one spread across the sky itself. Most of what your eyes notice is Andromeda's bright central region where stars gather densely up for their combined glow to survive the long passage to human vision. The greater galaxy extends far beyond that visible center. Its disk reaches outward through spiral structure, dust lanes, star-forming regions, old stellar populations, and faint outskirts that disappear into the background long before the galaxy truly ends. If all of that starlight were bright enough for unaided eyes, Andromeda would not look like a tiny smudge. It would stretch across a broad piece of the sky, spanning several times the width of the full moon. What seems small is not small at all. It is merely dim. Your eyes collect light for only a brief moment before the scene is renewed. A camera can remain open much longer, gathering faint photons that arrive one by one. As the exposure deepens, the apparent galaxy expands. Structures that were absent become visible, and what looked like empty sky begins to belong to Andromeda. And even that wider disk is not the whole object. Beyond the familiar spiral lies a looser realm of stars. Some move in extended streams, remnants of smaller galaxies pulled apart over long encounters. Farther out, thin populations of stars occupy a halo with no obvious boundary. Beyond them lies matter that gives off no light, known only through gravity and through the motion of everything held inside its influence. So the question of Andromeda's size begins to change almost as soon as we ask it. Are we measuring the bright region seen by the eye, the full stellar disk recorded by sensitive cameras, the outer streams left by earlier collisions, the reach of its satellite galaxies, or the dark matter halo whose gravity may extend far beyond the last stars we can easily map? Each answer describes a different Andromeda. Tonight, we will move outward through those answers one layer at a time. We will begin with the modest glow visible from Earth, then cross the structures that photographs reveal, the regions that telescopes detect only with patience, and the invisible architecture inferred from motion. Along the way, the galaxy will seem to grow, not because it is changing, but because our definition of its edge keeps moving. Andromeda has been above humanity for longer than any written record. For nearly all that time, it looked like a small cloud. Only in the early 20th century did we understand that the cloud was another galaxy, separate from the Milky Way, and filled with its own immense population of stars. Now a deeper recognition is taking shape. A galaxy is not an object with a clean border. It is a layered system whose visible beauty occupies only part of its real domain. The image most people know, with its luminous center and sweeping spiral form, is not false. It is simply incomplete. The hidden size of Andromeda begins where the picture fades. The first boundary around Andromeda was drawn by the human eye. For most of history, there was no photograph to reveal its spiral form, no instrument able to separate its stars, and no reliable way to measure the distance behind its pale appearance. There was only a dim patch in the sky, visible when the air was clear and the surrounding night was dark enough. That boundary was never the edge of the galaxy. It was the limit of human vision. Your eyes are remarkably sensitive, but they do not collect light indefinitely. They gather it for a fraction of a second, Send the signal inward and begin again. This allows you to notice movement, recognize shapes, and find your way through the world. It is less effective when the subject is a diffuse glow, spread across a large area of sky. Andromeda's light is not concentrated into a single point. It is distributed across a broad, tilted disk. The central region is bright enough to appear under good conditions, while the outer parts fade below the eye's threshold. This creates an illusion that has lasted for centuries. The galaxy looks compact because only its brightest region can be seen. Its real form continues far beyond the visible patch, but the outer light arrives too thinly for unaided sight to assemble it into an image. A star can appear obvious even when it is much farther away than another object, because its light is compressed into a point. A galaxy may produce far more total light while still being difficult to see, because that light is spread across a larger apparent area. Astronomers call this surface brightness. It describes how much light reaches us from each small portion of an extended object. A bright central core can stand out against the sky, while a broad outer disk containing billions of stars remains nearly invisible. The stars are there. Their combined light is arriving. It is simply distributed so widely that the background begins to swallow it. This is why a clear sky matters so much. Artificial light does not need to cover Andromeda directly to hide it. A brightened atmosphere raises the background glow across the entire sky. The galaxy's faint outer light then has less contrast against the air around it, until the difference becomes too small for the eye to recognize. Under city skies, even the central patch may disappear. Far from those lights, Andromeda begins to return. It may first appear only when you look slightly to one side, allowing a more sensitive part of the retina to receive its glow. Then, with patience, the small cloud holds its position while the sharper stars remain scattered around it. It does not become a grand spiral to the naked eye. It remains restrained, almost featureless. Yet, the act of seeing it carries an unusual scale. Nearly every individual star, visible without a telescope, belongs to the Milky Way. They are nearby members of our own galactic system, even when nearby still means hundreds or thousands of light years. Andromeda is different. Its faint light comes from beyond the Milky Way, from an entire stellar population gathered more than 2 million light years away. The eye cannot separate those stars. It receives them together long before anyone knew what that glowed its presence. In the 10th century, the Persian astronomer Abd al-Rahman al-Sufi described a small cloud in the constellation now associated with Andromeda. His description did not reveal another galaxy, but it preserved an accurate human observation. There was something diffuse among the fixed stars. That small cloud remained in the sky as generations changed beneath it. Later observers placed it in catalogues of nebulae, a word used for many hazy celestial objects whose true natures were not yet understood. Some nebulae were clouds of gas within the Milky Way. Some were clusters of stars. Others, including Andromeda, were galaxies at distances no available instrument could yet establish. The shared appearance concealed major physical differences. Through early telescopes, Andromeda became brighter and more extended, but it did not immediately surrender its identity. Its center looked smooth, because too many stars overlapped within each tiny region of the image. The spiral form could be photographed. Yet the question of where it belonged remained open. Was it a structure inside the Milky Way, perhaps part of our own galaxy's formation? Or was it something much farther away, a separate system comparable to the Milky Way itself? The answer depended on distance. Without distance, apparent size can mislead. A coin held near the eye can cover the moon. A small cloud nearby can occupy more of the sky than a continent viewed from orbit. To know the physical width of Andromeda, astronomers first had to discover how far behind its faint image the galaxy truly lay. That measurement became possible through a particular kind of star. Cepheid variables change brightness in a regular rhythm. Their cycles are not random flickers. The time required for a Cepheid to brighten and fade is connected to its true luminosity. Once that relationship had been established through the work of Henrietta Swan-Leavitt, astronomers gained a method for comparing how bright a Cepheid really was with how dim it appeared from Earth. The difference revealed distance. In 1923, Edwin Hubble photographed a region of Andromeda with the 100-inch Hooker telescope at Mount Wilson Observatory. On a glass plate, he identified a variable star that had first appeared to be a nova. He crossed out the earlier marking and wrote a new one beside it. The star became known as V1. Its changing light placed it far beyond the accepted scale of the Milky Way. Andromeda could no longer be contained inside our galaxy. The small cloud was a separate galaxy, and the visible universe became larger in a way that no wider photograph alone could have shown. The discovery did not make Andromeda expand. It changed the meaning of every part of the image. A faint central patch was now the blended light of an immense stellar system. Dark marks crossing its glow became lanes of dust on a galactic scale. Bright knots could be understood as regions where groups of young stars illuminated their surroundings. The outer haze was no longer a local mist. It was a distant disk seen at a steep angle. Once the distance was known, angular size could be translated into physical size. The geometry is simple in principle. An object with a known distance and a measured span across the sky must have a corresponding width in space. Deciding which span to measure is less simple, because Andromeda grows as observing methods become more sensitive. The naked eye sees the central glow. Binoculars reveal a longer oval. Telescopes and photographs uncover dust lanes and more of the disk. Deep surveys find stars beyond the familiar image. Each method draws a different contour, and none of those contours needs to be false. They represent different levels of brightness, different kinds of matter, and different definitions of belonging. This is the first lesson in measuring a galaxy. An edge may be created by the observer as much as by the object. A photograph has an exposure time. A telescope has a sensitivity range. A detector responds to certain wavelengths. A scientific survey chooses a threshold below which a signal is treated as background. Change any of these, and the apparent border may move. The same galaxy can therefore be assigned more than one diameter. One measurement may describe the bright stellar disk. Another may include faint, ultraviolet regions beyond it. Another may trace sparse stars in the outskirts. Still another may follow gravity into a region where almost no visible light remains. The familiar image of Andromeda is one useful answer, but it is not the final one. Seen from Earth, the galaxy is tilted by about 77 degrees, so we view its disk at a strong angle rather than face-on. This decompresses its circular structure into a long ellipse. Dust inside the disk blocks some of the light behind it, and the dense central bulge dominates the view. The result is a picture shaped by orientation, distance, dust, sensitivity, and the limits of perception. For a person standing beneath the sky, none of those complications need to be visible. The galaxy can remain a pale mark above the horizon, received without instruments and without calculation. Yet contained in that mark is a history of changing scale. It began as something the eye could barely hold. It became a nebula in a catalogue, then a spiral photographed on glass, then a separate galaxy, whose distance transformed the dimensions of the known cosmos. And now, with the distance established, we can begin moving across Andromeda itself. The small cloud has become a place. Once Andromeda becomes a place, its faint oval begins to separate into regions. At the center is a dense bulge of older stars. Around it lies a flattened disk crossed by lanes of dust, concentrations of gas, and broad patterns of stellar birth. Farther out, the organized spiral structure becomes thinner and less distinct, gradually blending into a more scattered population. This is the part of Andromeda that most closely matches the familiar idea of a galaxy. It is also the part most often measured when a diameter is given. Depending on the wavelength observed and the brightness threshold chosen, estimates for the visible disk commonly extend beyond 200,000 light-years from one side to the other. Some measurements place the span near 220,000 light-years. Others, tracing fainter features, reach closer to 260,000. The difference is not a disagreement about a solid wall. It reflects the fact that a galactic disk fades rather than stops. Imagine beginning near one outer edge and traveling toward the center at the speed of light. Even at that impossible pace, tens of thousands of years would pass before the central bulge began to dominate the view. The crossing would continue through the center and outward again for tens of thousands more. A message traveling across the full bright disk could require more than 200,000 years to complete the journey. During that time on Earth, entire human populations could rise, move across continents, develop new languages, and become ancestors of people living far beyond their memory. A signal beginning its passage, when early members of our species were already present, might still be crossing the galaxy, long after the individuals who sent it had disappeared into prehistory. This gives Andromeda an unusual kind of unity. We see it as one object, yet no event can be communicated instantly across it. One side does not know what is happening on the other side in any immediate sense. Gravity, light, and every other physical influence move through the system at finite speeds. The galaxy is held together, but not all at once. Its appearance in our sky deepens this effect. Andromeda is tilted sharply relative to our line of sight. We view its disk from the side at an angle of roughly 77 degrees. So a structure that is broadly circular becomes compressed into a narrow ellipse. If Andromeda faced us directly, its spiral patterns would be easier to trace. We would look down upon its disk in something closer to the way we see a whirlpool from above. Instead, the near side overlaps the far side. Dust clouds cross in front of stars behind them. Spiral features lie partially on top of one another from our perspective. The galaxy's depth becomes folded into a flatter image. Even so, the dust reveals some of that depth. Dark rings curve around the bright center, not because they contain an absence of matter, but because they contain matter that blocks visible light. Tiny grains of carbon-rich and silicate material gather inside cold clouds. Each grain is far smaller than anything the unaided eye could distinguish, yet across distances of thousands of light years, their combined effect becomes visible as broad shadows. The shadows allow astronomers to identify which side of the disk is closer to us. Dust on the near side lies in front of the glowing central bulge and therefore creates stronger dark bands. Dust on the far side is partly hidden behind the bulge's light. The imbalance gives the galaxy a three-dimensional orientation, even within a two-dimensional photograph. Behind those lanes, Andromeda's stars are not distributed evenly. The center holds a crowded population dominated by older, cooler stars. Their combined light gives the bulge a warmer, more yellow appearance in many visible light images. These stars have completed a large part of their lives without leaving the galaxy's central region, orbiting through a gravitational environment far more densely populated than the neighborhood around our sun. Moving outward, the stellar population changes. Young, hot stars appear in bluer concentrations. Clouds of hydrogen become illuminated by nearby stellar radiation. Supernova remnants expand into surrounding gas. Clusters form, age, and slowly disperse into the disk. One of Andromeda's most noticeable structures is not a perfectly drawn spiral arm, but a broad ring of gas and dust, roughly 30,000 light-years from the center. Astronomers often call it the 10 kiloparsec ring, using a unit common in galactic measurements. 1 kiloparsec is a little more than 3,000 light-years. So 10 kiloparsecs corresponds to about 33,000 light-years. Much of Andromeda's present star formation is concentrated there. In ultraviolet images, the ring becomes bright with young stars. In infrared observations, cooler dust glows in wavelengths human eyes cannot see. Radio telescopes trace atomic and molecular gas, revealing material that may later collapse into new stellar systems. The ring is not perfectly centered or perfectly circular. Its uneven form may preserve the effects of past gravitational encounters. A smaller companion galaxy, passing through or near Andromeda's disk, could have disturbed the gas and helped produce expanding patterns, much as a stone creates rings after entering water. The actual history is more complicated than that simple image, involving orbital motion, gravity, and a disk that was already structured before any encounter occurred. Still, the ring records motion on a scale difficult to notice from Earth. From here, it seems fixed. Within Andromeda, stars and gas are continually orbiting the galactic center. The journey is not rapid when measured against a human life, but the speeds are immense. Stars move at hundreds of kilometers per second, while requiring hundreds of millions of years to complete a broad circuit. A star can be moving faster than any spacecraft humanity has built and still appear almost motionless within the galaxy. This is the pace of a galactic disk. Movement becomes visible only across ages. The spiral patterns add another layer. A spiral arm is not simply a permanent chain of the same stars, traveling together like rail cars. Stars and gas move through patterns of higher density. Gas entering these regions can be compressed, making some clouds more likely to form stars. Young bright stars then help outline the pattern before aging and moving onward. The arm can persist as a recognizable structure, even while its individual contents change. A familiar comparison is a traffic slowdown on a highway. The region of congestion remains in roughly the same place for a while, although the cars entering it are not the same cars leaving it. In Andromeda, the scale is galactic, the participants are stars and interstellar clouds, and the timing unfolds over millions of years. But Andromeda's disk is not a clean example drawn in a textbook. Its spiral form is interrupted, distorted, and shaped by a history of encounters. The galaxy contains rings, broken arm segments, dust complexes, and regions whose motions point toward earlier disruption. Some of its present structure may have been reorganized by collisions with smaller galaxies. Other features may be connected to a much larger merger in its past. The disk is therefore more than a flat collection of stars. It is a record. Every uneven band, stream, and concentration carries information about gravity acting over time. A region rich in young stars tells one kind of story. A smooth population of older stars tells another. A distorted outer edge may preserve an encounter that ended before modern humans existed. Telescopes read these stories by separating the galaxy into wavelengths. Visible light shows stars and the shadows of dust. Ultraviolet light emphasizes hot young stars and recent star formation. Infrared observations pass through some dust and detect cooler material, as well as the glow of older stellar populations. Radio measurements follow hydrogen gas and molecular clouds. X-rays reveal hotter environments, including compact stellar remnants and gas heated to millions of degrees. No single image is the complete Andromeda. Each is a map of one physical component, made visible through one portion of the electromagnetic spectrum. Combining them is like sharpening a photograph, and more like assembling several related worlds into one understanding. A region that appears dark in visible light may glow in infrared. A smooth area in one wavelength may contain clusters in another. A bright optical center may conceal structures that become apparent only through careful measurements of stellar motion. This is why the measured size changes with the instrument. Ultraviolet surveys can trace young stellar populations into particular outer regions. Infrared detectors can follow older stars through dusty areas. Star counts can identify faint members of Andromeda even when their combined surface brightness is too low to form a continuous glow. At some point, counting individual stars becomes more useful than measuring the light between them. Andromeda is close enough for powerful telescopes to resolve many of its brightest stars separately. A photograph from a wide-field camera may look smooth, but a closer view breaks the haze into points. Each point has a brightness, a color, and a position that can be compared with models of stellar evolution. From these stars, astronomers estimate age, chemical composition, and distance. They can distinguish likely members of Andromeda from foreground stars in the Milky Way and from distant galaxies lying far behind it. The task is difficult because all three populations appear in the same direction. The image is layered not only within Andromeda, but across the universe. A star in the foreground may be a few hundred light-years away. A bright giant in Andromeda may be 2.5 million light-years away. A small reddish object nearby in the image may be a remote galaxy whose light has traveled for billions of years. They occupy neighboring pixels while belonging to entirely different scales. The observer must separate them through color, spectrum, motion, and statistical pattern. This careful sorting allows Andromeda's disk to be followed into regions where the continuous glow has almost vanished. Sparse stars still move in ways connected to the galaxy. Their chemical signatures resemble known populations. Their distribution aligns with broader structures extending from the inner disk. The apparent edge moves outward again, yet density continues to decline. The stars grow farther apart, and the orderly spiral pattern loses definition. The galaxy begins to look less like the bright object in photographs and more like an enormous field of scattered evidence. There is no final line engraved into space. There is only a gradual transition from crowded regions to thin ones, from a luminous disk to outskirts, where membership must be inferred one star at a time. For the listener resting beneath Earth's own sky, the entire structure remains compressed into that pale mark, the central bulge, the dusty ring, the blue clusters, the broad disk, and the long light crossing time all arrive together. Your eye does not receive them as separate chapters. It gathers their combined past into one dim presence. But beyond the disk, the galaxy is already becoming something less familiar. The spiral is ending. Andromeda is not. Beyond the last recognizable pieces of the disk, Andromeda becomes harder to picture. There are still stars here, but they no longer form a bright continuous surface. They are spread through an enormous, roughly rounded region surrounding the galaxy, a region so thin that most of it would look empty even from within. This is Andromeda's stellar halo. The word halo can suggest a neat ring, but the real structure is neither thin nor perfectly smooth. It reaches above and below the disk, filling a much larger volume than the spiral itself. Its stars are sparse, its boundaries uncertain, and its shape has been disturbed by a long history of smaller galaxies falling inward. The bright disk may extend a little more than 200,000 light-years across, depending on how it is measured. The stellar halo can be traced for several 100,000 light-years from the center. In some directions, it occupies more space while producing far less light. That contrast is one of the most useful ways to understand the hidden size of a galaxy. Brightness does not tell us how much room a structure fills. A dense central bulge can dominate a photograph, while a much larger halo remains almost absent from the image. Inside the halo, the average distance between stars is far greater than it is in the disk. There are no broad, luminous arms and few clouds capable of forming new stars. Most halo stars are old. Many contain smaller proportions of elements heavier than hydrogen and helium, suggesting that they formed early, before repeated generations of stars had enriched their surroundings. They are not all the same age or composition. Some appear to have formed within Andromeda, others were born in smaller galaxies and entered the halo later, carried there by mergers that slowly dismantled their original homes. This mixture turns the halo into a record of assembly. A galaxy does not always grow by drawing diffuse gas inward and forming stars in place. It can also grow by absorbing other galaxies. Large systems gather smaller ones over billions of years. The process may sound suddenly described as a collision, but many of these encounters unfold across several orbits and hundreds of millions of years. A small galaxy approaching Andromeda first feels an uneven gravitational pull. The side facing Andromeda is attracted a little more strongly than the far side. That difference creates a tidal force. Stars begin to stretch away from their former arrangement. The small galaxy may survive its first passage, then return on another orbit, losing more material each time. Eventually, its identity can fade. Its stars do not disappear. They are redistributed. Some form long streams that curve through the halo. Others gather into broad shells or faint clouds. Given it enough time, those features spread and overlap, becoming increasingly difficult to distinguish from the general population. Andromeda is surrounded by many such traces. One of the most prominent is commonly called the Giant Stellar Stream. It extends across a large region southeast of the galaxy's center and contains stars whose motions and chemical properties point toward a shared origin. It is not a stream of gas flowing like water. It is a population of stars moving along related paths after their parent galaxy was pulled apart. The stream is longer than the distance from the Sun to many of the stars visible in our night sky by thousands of times. Yet from Earth, it cannot be seen as a bright ribbon. Its surface brightness is too low. Astronomers find it by taking deep images separating likely Andromeda stars from foreground stars in the Milky Way and looking for slight increases in the number of stars across wide fields. What seems empty at first begins to show structure when the counting becomes precise enough. The method is patient. A telescope records many points of light. Some belong to our own galaxy. Some are stars in Andromeda's halo. Others are remote galaxies whose compact shapes resemble stars in an image. Color, brightness, spectra, and motion help divide them into populations. Once the foreground is removed statistically, a faint pattern remains. That pattern may be a stream. Another field may reveal a shell. A third may show a diffuse cloud whose stars share a similar chemical history. The halo becomes visible not as a single photograph, but as an arrangement of evidence. This is a different way of seeing from the one that revealed the spiral disk. The disk can announce itself through combined light. The halo often requires individual stars to be identified and mapped over large areas. The galaxy is no longer a bright object against a dark background. It is a probability spread across the sky. Each likely member adds a small amount of confidence. Thousands of such stars draw an arc. Millions begin to reveal a past encounter. The farther outward the search moves, the more difficult the separation becomes. Andromeda's halo stars grow rarer, while the foreground of the Milky Way remains. Background galaxies continue to fill the same direction. Measurement errors become more important, and the definition of membership becomes more cautious. There is no moment when a detector reaches a final wall. Instead, the density of Andromeda's stars gradually approaches the density of everything else in the field. The edge is where the signal becomes too faint to distinguish, not necessarily where the galaxy's influence ends. Globular clusters provide another set of markers. These are compact, roughly spherical gatherings of old stars, often containing hundreds of thousands of members. Many orbit far outside the bright disk. Some appear along stellar streams, suggesting that they once belonged to smaller galaxies later absorbed by Andromeda. A globular cluster can survive after the galaxy around it has been stripped away. Its stars are packed closely enough for the cluster to remain bound while the larger system dissolves. It continues through the halo as a surviving fragment, carrying information about where it formed and what kind of galaxy once held it. Andromeda has a rich population of these clusters. Some lie near the disk. Others travel through the outer halo at distances that make the familiar spiral seem like only the center of a much wider system. Their motions help astronomers estimate the mass enclosed within their orbits, including matter that cannot be seen directly. The clusters are therefore both relics and measuring instruments. They remember earlier galaxies, and they respond to the present gravitational field. Streams perform a similar role. A stream does not follow a random path. Its curve and speed are shaped by the distribution of mass around Andromeda. If the halo contains more mass, the orbit bends in one way. If the mass is arranged differently, the stream takes another course. By comparing observed streams with computer models, astronomers can test possible histories. They can ask what kind of smaller galaxy entered Andromeda, how massive it was, how close it passed to the center, and how many orbits were needed to produce the structures seen today. No model recovers every detail with perfect certainty. The stars have been moving for a long time, and more than one encounter may have contributed to the same region. A feature that looks like a single stream in one map may contain several populations layered together. The halo is not a clean archive with each event stored on a separate page. It is more like writing that has been placed over older writing. Some lines remain clear, others are partly erased, many cross one another. Even so, the overall message is unmistakable. Andromeda has grown by consumption. The galaxy visible today is not simply the larger version of one original disk. It is the result of repeated additions. Some were small and left only narrow traces. Others may have rearranged the disk itself, altered the central regions, or produced broad populations now mixed throughout the halo. This history helps explain why the outskirts are uneven. A halo formed only from stars, born in a single early collapse, might appear smoother. Andromeda's halo contains pronounced substructure, including streams, shells, and concentrations that have not yet fully dispersed. Their continued visibility means that some mergers were recent enough, in galactic terms, for the debris to remain recognizable. Recent in this context may still mean billions of years. A stream can preserve coherence long after continents have shifted and species have appeared and vanished on Earth. Galactic memory is written in orbits, and an orbit around Andromeda can require hundreds of millions or even billions of years in the outer regions. There is a calmness in that scale. The stars do not need to remain close together to preserve a relationship. They can be separated across an immense arc and still carry similar motions, similar compositions, and the shared signature of a home that no longer exists. Astronomers recognize the family after the house is gone. This is one of the quieter forms of cosmic archaeology, No one watches the original galaxy fall apart from beginning to end. The event is reconstructed from what remains. A cluster, a stream, a change in metallicity, and a curve through the halo become clues to a history that unfolded before human observation began. The work connects many generations of looking. Early observers recorded the central glow. Photographers revealed the disk. Wide-field surveys later found the low-brightness structures around it. Future instruments will trace fainter stars and measure their motions more precisely, adding new detail to a map that is still unfinished. The object has not changed during that sequence. Our ability to recognize its outer pieces has, and so Andromeda grows again, not in physical size, but in the territory we understand the sand as belonging to it. The bright spiral remains at the center, carrying most of the light people associate with the galaxy. Around it lies a much larger stellar environment, assembled from disrupted companions, old clusters, diffuse populations, and streams that curve through space beyond the limits of familiar photographs. If the disk is the part of Andromeda that can be seen as a place, the halo is the part that must be read as a history. Its stars are too scattered to form a clear surface. Together, they show how far the galaxy has reached into the past. And beyond those stars, another boundary waits. It cannot be mapped by light alone. Gravity continues farther than starlight, beyond Andromeda's scattered halo stars, beyond the streams and clusters that can still be counted. There is a much larger structure that cannot be photographed in the ordinary sense. It produces no visible glow. It casts no shadow across the galaxy. It does not gather into bright clouds or resolve into distant points. Its presence is known through motion. Stars orbit Andromeda's center. Clouds of hydrogen circle through the outer disk. Globular clusters travel along wide paths, and satellite galaxies move through the surrounding volume. None of them decides its own course. Each responds to the combined gravitational pull of all the mass inside and around its orbit. By measuring those movements, astronomers can weigh what they cannot see. The result is a galaxy much larger than the one drawn by light. Near the center, Andromeda's stars are densely concentrated. It would be reasonable to expect most of the galaxy's gravitational mass to be concentrated there as well. If that were true, objects farther from the center should orbit more slowly, much as the outer planets move more slowly around the Sun than the inner planets do. Mercury completes its orbit quickly because it lies deep within the Sun's gravitational field. Neptune travels at a lower speed because it is much farther away, beyond most of the Sun's mass. The pull weakens with distance in a predictable way. A spiral galaxy does not follow that pattern. As astronomers trace the motion of gas and stars outward through Andromeda's disk, the orbital speed does not fall as sharply as the visible matter alone would suggest. The outer regions continue moving rapidly, as though they are enclosed within far more mass than the bright stars, gas, and dust can provide. This pattern is called a rotation curve. It is a simple-looking graph with a deep implication. Distance from the galactic center runs along one direction, orbital speed runs along the other. The curve rises through the inner region, then remains comparatively level across much of the disk instead of dropping away. Something continues to supply gravity beyond the brightest parts of the galaxy. Under the standard cosmological interpretation that something is dark matter, the name does not describe a darkness that could be seen. It describes matter that does not appear to emit, absorb, or reflect light in the ways ordinary matter does. It reveals itself primarily through gravity and through the larger cosmic structures that gravity helps create. What dark matter is made of remains unknown. It may consist of a kind of particle not yet detected directly in a laboratory. Many candidates have been proposed, and experiments continue to search for evidence. No single candidate has yet been confirmed as the answer. The uncertainty concerns its identity, not the gravitational patterns astronomers are trying to explain. Across galaxies and clusters of galaxies, visible matter often moves as though additional mass is present. Light from distant objects can be bent by gravity in ways that reveal more mass than telescopes can see. The growth of cosmic structure also points toward a large non-luminous component. Andromeda offers a nearby example. Its stars, gas, streams, clusters, and companions move through a gravitational field extending far beyond the luminous spiral. The simplest broad picture places the visible galaxy inside an enormous dark matter halo. This halo is not thought to be a hollow shell surrounding the disk. Dark matter would pass through the region occupied by stars as well. Its density is expected to be greatest toward the inner galaxies and to decline outward, spreading through a roughly spherical or mildly stretched volume. The word spherical is an approximation. Real halos can be distorted by their formation histories, by nearby galaxies, and by material still falling inward. Andromeda has absorbed smaller systems, and each encounter may have altered the distribution of matter around it. The Milky Way and other members of the local group also contribute gravitational pulls. There may be no perfectly balanced shape to find. Still, the halo is far rounder than the thin stellar disk embedded within it. If Andromeda's disk were imagined as a broad sheet, the dark matter halo would surround it in 3 dimensions, reaching far above and below the plane. The familiar spiral would occupy only the bright interior of a much larger gravitational domain. This changes the meaning of diameter once again. A disk diameter can be measured from one fading edge of starlight to another. A dark matter halo does not offer an equivalent line. Its density declines continuously, and dark matter from nearby structures may eventually blend into the wider matter distribution of the local group. Astronomers therefore use defined boundaries. One common choice is called a virial radius. The term refers to a region inside which matter is dense enough, according to a chosen cosmological definition, to be treated as part of the galaxy's gravitationally assembled halo. It is not a physical wall. A particle crossing this radius would encounter no sudden surface. Nothing would change color. There would be no sign marking the end of Andromeda. The radius is a scientific convention placed upon a gradual transition. Different studies may use slightly different density thresholds, assumptions, and models. As a result, the estimated halo size and mass can vary. Current measurements generally place Andromeda's virial radius at hundreds of thousands of light years from its center, several times the radius of the bright stellar disk. A representative estimate is around 700,000 light-years from the center, though the uncertainty is substantial. Measured from one side of the halo to the other, that would produce a diameter approaching 1.5 million light-years. The precise number should not be mistaken. For a discovered outer surface, it is a useful description of scale, built from a model of how mass is distributed. Even with that caution, the comparison is striking. The bright galaxy, seen in photographs, may span a little more than 200,000 light-years. Its dark matter halo may occupy a region several times wider, enclosing a volume hundreds of times greater than the volume of the visible disk. Andromeda's luminous form is therefore not the container of the galaxy. It is something contained. The stars are a bright population living inside a larger gravitational environment. To estimate the mass of that environment, astronomers combine several kinds of motion. The inner rotation curve traces gas and stars within the disk. Farther out, globular clusters and planetary nebulae can serve as markers. Stellar streams respond to the shape of the gravitational field. Satellite galaxies provide information at even greater distances. Each tracer has limitations. A stream may have been disturbed by a past encounter, A satellite may be arriving for the first time rather than following a settled orbit. Measurements often capture only the motion toward or away from Earth, leaving sideways motion more difficult to determine. The galaxy itself may not be in perfect equilibrium after earlier mergers. These uncertainties create a range of possible masses. Many studies place Andromeda's total halo mass on the order of 1 trillion times the mass of the Sun. Some estimates are lower, others are higher. The disagreement is not small enough to ignore, but all credible values lead to the same broad conclusion. Most of Andromeda's mass is not contained in the stars we see. Ordinary matter still creates the image. Stars produce nearly all its visible light. Gas forms clouds and future stars. Dust shapes the dark lanes. Stellar remnants, planets, and compact objects add mass without contributing much brightness. But even when these are counted, they do not fully account for the observed motions. Dark matter dominates the larger balance. A trillion solar masses is difficult to hold as a single idea. The Sun already contains more than 300,000 times the mass of Earth. Andromeda's halo may contain the gravitational equivalent of roughly 1 trillion suns, spread through a region so large that much of it remains almost empty by everyday standards. Dark matter is not expected to form planet stones or clouds like ordinary matter. It does not appear to lose energy through light and settle into a thin rotating disk. Instead, its particles would continue moving along extended orbits, passing through the halo and through one another with very little direct interaction. At this moment, dark matter associated with the Milky Way is thought to be moving through Earth and through every person on it. There is no sensation of its passage. If dark matter particles interact only weakly with ordinary material, enormous numbers could cross a body without leaving any noticeable trace. Sensitive detectors place deep underground search for rare interactions that might reveal what those particles are. The search continues beneath mountains while the evidence remains written across galaxies. Andromeda's rotation is part of that evidence. There is another way to think about what the dark halo does. It is not merely additional weight added after the visible galaxy formed. In modern models of cosmic evolution, dark matter helps provide the gravitational framework in which ordinary gas gathers. Early concentrations of dark matter attract gas. The gas cools, collapses, and eventually forms stars. Small structures merge into larger ones, building galaxies over billions of years. The halo is therefore part of Andromeda's origin. Its gravity helped collect the material that became the stellar disk. It guided smaller galaxies inward. It continues to shape the paths of streams, clusters, and satellites. The visible Andromeda is, in part, a response to an invisible structure. Change the dark matter halo, and the galaxy's history would change with it. A less massive halo might have captured fewer companions. A differently shaped halo would bend streams onto different paths. A different distribution of mass could alter the disk's rotation and its response to encounters. Astronomers use these relationships in reverse. They observe the visible motions and ask what invisible arrangement would produce them. A stream curving through the outskirts, becomes a line drawn by gravity. A dwarf galaxy moving around Andromeda becomes a test particle on a scale of hundreds of thousands of light years. A cloud of hydrogen circling the disk becomes part of a balance between inward gravitational pull and outward motion. Together, these tracers build a map with no light of its own. The map is not finished. The shape of Andromeda's dark halo remains uncertain. Its exact mass depends on how the motions are modeled. Its outermost regions are influenced by the rest of the local group, making it difficult to decide where the halo becomes the space between galaxies. There are also alternative ideas that attempt to explain galactic motions by modifying our understanding of gravity rather than adding unseen matter. Such models can reproduce some rotation patterns, but they must also account for gravitational lensing, galaxy clusters, the early universe, and the formation of large-scale structure. For now, dark matter remains the central framework used to interpret Andromeda's extended gravitational field. Within that framework, the galaxy has no simple end. Far from the bare bright disk, the dark matter density becomes lower. At some distance, Andromeda's gravitational influence competes with the Milky Way, the Triangulum Galaxy, smaller companions, and the wider mass of the local group. The halos of galaxies are not isolated bubbles placed in empty space. They formed within a connected universe, filaments of matter guide galaxies into groups. Smaller halos enter larger ones. Material can be stripped, exchanged, or left, moving through the region between major galaxies. The boundary of one system may depend on the presence of another. Andromeda is about 2.5 million light-years from the Milky Way. If its halo extends hundreds of thousands of light-years from its center, and the Milky Way possesses a halo of comparable scale, then the distance between their outer gravitational regions is much smaller than the distance between their bright disks. The two galaxies remain separated. Their stars are not yet intermingling, yet they are not two luminous islands surrounded by absolute emptiness. They belong to a shared gravitational neighborhood, and their motions have been connected for billions of years. Every estimate of Andromeda's halo is therefore also part of a larger problem. To weigh Andromeda, astronomers must understand its satellites. To understand the satellites, they must consider the Milky Way. To describe both large galaxies, they must account for the local group as a whole. Scale widens into relationship. From Earth, Andromeda can still fit within the view of an outstretched hand. Its bright center remains a dim blur, and its spiral disk remains hidden from ordinary sight. Around that blur is a stellar halo built from lost galaxies. Around the stellar halo is a darker structure many times wider, and within that structure, every visible star follows a path shaped by mass it cannot illuminate. The picture has faded, but the galaxy's gravity keeps going. Far beyond the visible disk, Andromeda is surrounded by smaller galaxies. Some are bright enough to appear in ordinary telescope images. Others are so diffuse that their stars must be counted individually before the galaxy itself becomes recognizable. Together, they form a population of companions moving through Andromeda's extended gravitational field. These companions offer another way to ask how large the galaxy really is. A galaxy can be measured by its stars. It can be measured by its dark matter, or it can be measured by the smaller systems that remain bound to it, traveling around the larger galaxy like distant members of a widely scattered family. The most familiar companions are M32 and M110. Both can be seen near Andromeda in photographs, appearing as small elliptical patches beside the great tilted disk. Their proximity in the image makes them look almost attached to it, though each is a separate galaxy with its own stars, history, and gravitational identity. M32 is compact. Its stars are crowded into a relatively small volume, giving it a high surface brightness compared with many dwarf galaxies. It lies projected close to Andromeda's disk and may have been altered by repeated gravitational encounters with the larger galaxy. Its outer stars may have been stripped away. Its internal structure may have been compressed or reshaped. The details remain a subject of study, but its present form suggests that closeness to Andromeda has not been without consequence. M110 is more extended. It appears smoother and more diffuse, with evidence of dust and past star formation, despite its elliptical appearance. Like M32, it is caught within Andromeda's gravitational environment, but its history has followed a different path. The two companions show that there is no single way for a small galaxy to live near a large one. One may become compact, Another may be stretched. A third may lose gas. A fourth may be pulled apart almost completely. The outcome depends on mass, orbit, internal structure, and how closely the smaller galaxy passes to Andromeda's center. Many of Andromeda's companions are dwarf spheroidal galaxies. These systems contain relatively few stars. Compared with a major spiral, they have little remaining gas and almost no present star formation. Their light is spread thinly across the sky, making them difficult to detect, even when they are not extremely far away. A dwarf spheroidal may contain millions of stars and still appear almost empty. Its stellar population can be so sparse that a photograph does not show a continuous glow. Instead, astronomers identify an unusual concentration of stars, sharing similar distances and colors. The galaxy appears through statistics before it appears through light. Some of these dwarfs are among the faintest known galaxies. Their visible matter contributes only a small part of the mass inferred from the motions of their stars. Dark matter appears to dominate them strongly, helping their scattered stellar populations remain gravitationally bound. This makes the companions useful laboratories. Within Andromeda itself, stars, gas, dust, and dark matter overlap in a complicated system. In a small dwarf spheroidal, there may be relatively little gas and a simpler stellar structure. By measuring how quickly its stars move, astronomers can estimate how much unseen mass is required to hold the system together. The dwarf becomes a small-scale test of the same invisible framework surrounding the larger galaxy. Yet proximity to Andromeda complicates the measurement. A satellite passing through a strong tidal field may not be in a stable state. Some of its stars may already be escaping. If the system is being stretched, its internal motions can make it appear more massive than it would in isolation. The observer must decide whether the stars are orbiting peacefully within the dwarf or being pulled away by Andromeda. Often, the answer contains some of both. The satellites do more than reveal their own mass. Their positions and velocities help define the reach of Andromeda's gravity. A companion hundreds of thousands of light years from the center may still be orbiting within the larger halo. Another object at a similar distance may be moving through the local group without being permanently bound to Andromeda at all. Distance alone does not settle the question. Motion matters. To decide whether a galaxy belongs to Andromeda's satellite system, astronomers compare its position, speed, direction of travel, and likely orbital history. The mass assigned to Andromeda's halo changes the answer. A more massive halo can hold fast-moving companions at greater distances. A less massive halo cannot. This creates a kind of circular problem. The satellites are used to estimate Andromeda's mass, but their membership depends partly on what that mass is assumed to be. Researchers approach the problem through models. They test different halo masses and reconstruct possible orbits. They compare the present arrangement with computer simulations of how galaxy groups form. They examine which companions could have remained bound over billions of years and which may be recent arrivals. No single satellite provides a final answer. Together, they narrow the possibilities. Their distribution is not perfectly random. A number of Andromeda's dwarf companions appear to lie within a relatively thin extended arrangement, sometimes described as a plane of satellites. Several also appear to share a common sense of motion along that structure. The pattern is intriguing because standard models of galaxy formation often produce satellite populations with broad, uneven distributions rather than a single, thin, rotating plane. But the interpretation is not settled. Some alignments can arise temporarily. Observational surveys do not detect every faint galaxy equally in every direction. The sideways motions of distant dwarfs are difficult to measure, and a structure that appears coherent from one viewing angle may be less stable when full three-dimensional motion is considered. The plane may preserve a shared history, perhaps involving companions arriving together along a larger filament. It may be connected to an earlier interaction, or part of the apparent order may be temporary. The uncertainty is scientifically useful. It reminds us that a galaxy's surroundings are not a finished arrangement. Satellites are continually moving. Some may have orbited Andromeda many times. Others may be approaching for the first time. The system we see is a single moment inside a long gravitational process. Among Andromeda's neighbors, the Triangulum Galaxy holds a special position. Also known as M33, it is the third largest major galaxy in the local group, after Andromeda and the Milky Way. It lies several 100,000 light-years from Andromeda, close enough for the two galaxies to influence one another, yet large enough to possess its own substantial disk, star-forming regions, and dark matter halo. Whether Triangulum should be described as a satellite of Andromeda depends on the definition being used. It may be gravitationally bound to Andromeda. It may have passed near the larger galaxy in the past. Some models suggest a previous close encounter, while others allow an orbit that has not yet brought the galaxies so near. Measurements of their motions continue to refine the possibilities. Triangulum is not simply another small dwarf. It is a galaxy with tens of billions of stars, large enough to shape the local group rather than merely respond to it. If it is bound to Andromeda, then Andromeda's effective system reaches across a remarkable distance. The bright disk would be only the central structure of a galactic family extending through hundreds of thousands of light years, perhaps including another spiral galaxy of its own. This does not mean that every star between Andromeda and Triangulum belongs to one continuous object. The region is mostly empty. The connection is gravitational, not luminous. Two galaxies can remain distinct while moving inside the same larger arrangement. This is common across the universe. Galaxies gather into groups and clusters. Their halos overlap. Smaller systems orbit larger ones. Gas is stripped, stars are exchanged, and gravitational relationships evolve over time. The individual galaxy remains useful as a concept, but nature does not always honor the clean separation suggested by a catalogue. Andromeda has its own identity. Triangulum has its own. The Milky Way has its own. Yet all three move within the local group, a collection containing dozens of known galaxies spread across a region roughly 10 million light-years wide. Most members are dwarfs. The Milky Way and Andromeda dominate the mass. Adds another major center of gravity. Around them, smaller galaxies follow paths shaped by the group as a whole. At large distances, it becomes difficult to say where one galaxy's domain ends and the local group begins. A dwarf near Andromeda may respond mostly to Andromeda. A dwarf between the two large spirals may feel both. Another on the edge of the group may be only loosely attached, moving near the boundary between the local group and the wider cosmic environment. These relationships are not permanent. A satellite can lose energy through gravitational interactions and fall inward. Another can be accelerated and thrown onto a wider orbit. A close encounter between galaxies can transfer material from one system to another. Over billions of years, membership can change. The present satellite system is therefore not simply a collection of objects around Andromeda. It is a record of arrival, survival, and loss. Some dwarfs may have fallen near the larger galaxy. Others may have entered its halo later. Several have already been disrupted, leaving only streams. More may be in the early stages of that process now. The companions that remain visible are not the complete population Andromeda has ever possessed. They are the survivors. Computer simulations suggest that many dark matter sub-batellows may orbit a large galaxy without forming enough stars to become easily detectable. Some may contain only a tiny stellar population. Others may be entirely dark, their ordinary matter, lost or never gathered efficiently. If such subhalos surround Andromeda, then even its known satellites reveal only part of the structure. The galaxy may be accompanied by invisible companions moving within the larger, invisible halo. Their gravity could disturb stellar streams or alter the motions of visible systems. Astronomers search for these effects, hoping that a gap, bend, or unusual concentration in a stream might reveal the passage of something that cannot otherwise be seen. A missing section of stars can become evidence for an unseen object. Again, Andromeda's size is inferred through what it does. Its halo shapes orbits, its tides stretch dwarfs, its gravitational field guides triangulum, its hidden substructure may disturb streams. The galaxy extends into every motion connected to it. There is no single photograph capable of holding all of this. A visible light image may show M32 and M110 near the disk. A deeper survey reveals faint dwarf galaxies farther away. A map of stellar streams adds the remains of companions that no longer survive as intact systems. A dynamical model fills the surrounding volume with dark matter and possible dark subhalos. Each layer expands the family. From Earth, the companions appear separated by patches of sky. That separation can be misleading. An angle measured across the sky becomes an immense physical distance at Andromeda's location. Two objects that seem close in a photograph may be tens of thousands of light years apart along our line of sight. Another that appears farther away on the sky may occupy a similar three-dimensional distance from the center. The image flattens the system. Astronomers rebuild its depth through distance measurements. Variable stars provide one method. The brightness of the red giant branch provides another. Stellar populations, spectra, and geometric relationships help refine the map. Each distance contains uncertainty, and those uncertainties affect the reconstructed arrangement. A satellite can shift from the near side of the halo to the far side within the allowed range of a measurement. Its likely orbit can change with it. This is why Andromeda's outer system remains an active field of study. The central galaxy is easy to identify. The extended family is not. New faint companions can still be found. Improved measurements can change which objects are considered bound. Better simulations can reveal histories that earlier models missed. The hidden size of Andromeda is not only a number waiting to be measured more precisely. It is a changing scientific definition. Does the galaxy end where its disk fades? Where its last halo stars can be counted? Where its satellites cease to remain bound? Where its dark matter density blends into the local group? Each boundary answers a different question. The satellite system gives one of the widest practical answers. It treats Andromeda not only as a spiral of stars, but as the central influence within a population of smaller galaxies. Seen this way, the bright disk is less like the whole galaxy and more like the inhabited center of a much larger territory. Far beyond it, companions continue along slow paths. Some will remain separate for billions of years. Some will lose stars. Some will disappear into streams. And every orbit quietly traces the reach of the galaxy they surround. There is another Andromeda beyond the stars. It surrounds the bright disk, the stellar streams, and many of the satellite galaxies. It contains ordinary matter rather than dark matter, yet it remains almost entirely unseen. This outer envelope is made of gas. Astronomers call it the circumgalactic medium, a broad region of diffuse material lying around a galaxy and beyond the denser gas between its stars. It is not a second atmosphere in the planetary sense. There is no clear lower surface, no weather, and no boundary where a traveler would suddenly enter it. The gas is spread too thinly for that. A particle could travel a great distance before encountering another. Even so, across hundreds of thousands of light years, This nearly empty material adds up. It holds matter, energy, and traces of the galaxy's history. The circumgalactic medium is where Andromeda exchanges material with the space around it. Gas can fall inward from the wider universe. Material expelled by stars can move outward into the halo. Smaller galaxies can lose gas as they pass through it. Some atoms may circulate for billions of years before returning to the disk, while others may leave the galaxy's denser regions and never come back. The visible spiral is therefore not a closed system. It breathes across a scale much larger than the photograph suggests. This process does not resemble breathing in any rapid or regular sense. There is no single expansion and contraction. Instead, material moves along many paths at once. Cold gas can enter, hot gas can rise. Supernova explosions can push enriched material away from the disk. Gravity can slow that material and draw part of it back. The galaxy continually exchanges matter between its central regions and its outskirts. Much of this gas is ionized. Its atoms have lost one or more electrons after being heated or exposed to energetic radiation. In that state, the material is often called plasma. It may reach temperatures from tens of thousands to millions of degrees, yet remain difficult to detect because its density is so low. Temperature and warmth are not quite the same experience here. A single particle can carry considerable energy and still have almost nothing nearby with which to share it. A human body placed in such a region would not feel a surrounding heat in the way it would inside warm air. The gas is hot by the motion and energy of its particles, but thin beyond ordinary comparison. Andromeda's gaseous halo cannot be mapped by simply pointing a camera at it. There is too little visible light. Instead, astronomers use more distant objects as background lamps. Far behind Andromeda lie quasars, intensely luminous regions surrounding supermassive black holes in remote galaxies. Their light crosses billions of light years before reaching us. On the way, some of it passes through Andromeda's extended halo. The gas leaves marks in that light. Certain atoms and ions absorb particular wavelengths. When the quasar's spectrum is separated into its component colors, these absorptions appear as narrow missing regions. The quasar provides the light. Andromeda's halo provides the shadow. By observing many quasars positioned around the galaxy, astronomers can test different paths through the surrounding gas. One sightline passes relatively close to the bright disk. Another crosses a more distant region. A third lies far beyond the visible spiral, but still carries the absorption signature of material associated with Andromeda. Each quasar is like a small light placed behind an invisible shape. One light cannot reveal the whole outline. Many begin to form a map. Using the Hubble Space Telescope, researchers examined dozens of quasar sightlines passing through the region around Andromeda. The resulting measurements indicated that the gaseous halo extends at least about 1.3 million light-years from the galaxy in many directions. In some directions, detectable material may reach as far as 2 million light-years. The numbers are so large that the distance between the Milky Way and Andromeda begins to look different. Their bright disks remain about 2.5 million light-years apart. But if Andromeda's diffuse gas extends more than 1 million light-years from its center, and the Milky Way has a large gaseous halo of its own, then the outer envelopes may already approach one another. They may even overlap. This does not mean that the two spiral disks are already colliding. The stars of Andromeda remain far away. Its dust lanes do not cross the Milky Way. Its central bulge is still a distant mark in our sky. What may be meeting are the most diffuse outskirts, where atoms are separated by great spaces and where the idea of one galaxy ending before another begins becomes difficult to maintain. At that scale, the space between galaxies is not empty. It contains gas, dark matter, radiation, magnetic fields, energetic particles, and material connected to the local group as a whole. Some of it may be clearly associated with Andromeda. Some may belong more naturally to the Milky Way. Other material may occupy the region between them. Without offering a simple membership, the boundary becomes a of motion, composition, and interpretation. The gaseous halo appears to have more than one broad layer. Closer to Andromeda, within roughly 500,000 light-years, the gas is more complex. It shows a greater variety of ionization states and structure. This inner region is more directly affected by the galaxy's disk, where stars form, age, and release material. Farther out, the halo appears smoother and hotter. The change is gradual, but it suggests different levels of connection to the active galaxy within. The inner circumgalactic medium receives the effects of stellar life. Massive stars emit radiation and stellar winds. Some end in supernova explosions that drive expanding waves through surrounding gas. Groups of supernovae can help create large outflows, rising above and below the disk. These outflows carry ordinary matter away from the places where stars formed. Hydrogen and helium dominate the material, but the gas also contains heavier elements created inside stars. Astronomers use the word metals for every element heavier than hydrogen and helium. Oxygen, carbon, silicon, iron, and many others belong to this category, even though their everyday properties are very different. Their presence in Andromeda's halo reveals a journey. The early universe produced mostly hydrogen and helium, with a small amount of lithium. Heavier elements were built later through stellar processes. Some formed during the long lives of stars. Others were created or dispersed during stellar deaths. When those elements appear far outside a galactic disk, they show that the products of stars have traveled. An oxygen ion detected hundreds of thousands of light-years from Andromeda's center may once have been part of a star. It may have been released into the interstellar medium. A supernova or a series of energetic events may have helped push it outward. It may now remain suspended in the circumgalactic medium, moving through a region too faint to see directly. The halo is not untouched material surrounding the galaxy. It has been altered by the galaxy it surrounds. At the same time, the halo may contain gas that has not yet entered the disk. Material from the wider cosmic web can fall toward a galaxy under gravity. As it approaches, it may be heated, slowed, mixed, or divided into streams and clouds. Some of this gas could eventually help form new stars. Before a star can begin, ordinary matter must gather. A galaxy that continues forming stars must therefore maintain access to gas. The supply inside the disk is not limitless. Star formation locks some matter into long-lived stars and remnants. Other material is blown outward. The circumgalactic medium becomes a reservoir. It can receive material from the disk and provide material to it. This relation is one reason the halo matters so much to galactic evolution. A galaxy cannot be understood only by counting its stars. Its future depends partly on gas that has not yet become visible. Andromeda forms stars more slowly today than it did during some earlier periods. Its disk still contains regions of stellar birth, especially along the prominent ring. But the galaxy has moved away from the more active state, seen in many blue spiral galaxies. Its gas supply, merger history, and internal structure all contribute to that change. The circumgalactic medium may preserve evidence of the transition. Outflows carry the chemical record of earlier star formation. Incoming gas affects how much new material becomes available. Interactions with satellites disturb both the halo and the disk. The outer gas becomes part of the explanation for what the bright galaxy is doing now. It also affects the companions moving through it. A small satellite entering Andromeda's halo does not travel through a perfect vacuum. Its own gas encounters the diffuse plasma around the larger galaxy. Even an extremely thin medium can matter when the encounter continues across tens of thousands of light years. The satellite's gas feels pressure. Material can be pushed backward and stripped away, particularly if the smaller galaxy has weak gravity. Stars are much harder to remove through this process because they do not behave like a connected fluid. Gas clouds, however, interact with the surrounding medium. A dwarf galaxy may therefore lose the material needed for future star formation while retaining many of its existing stars. It can become faint and inactive. The gaseous halo helps shape the population of satellites, even when it cannot be seen beside them. This pressure is sometimes compared with the wind felt by a moving object, though the galactic version is far thinner and longer lasting. The satellite moves through plasma, and the plasma moves relative to the satellite. Across cosmic time, the interaction can remove a substantial amount of gas. Gravity and pressure work together. Andromeda's tides pull on stars and dark matter. Its circumgalactic medium pushes on gas. The companion is altered by the full environment of the larger galaxy. Once again, the hidden size of Andromeda becomes a question of consequence. How far from the center can the galaxy change another object? How far away can its gas be detected? At what distance does material still carry Andromeda's chemical and dynamical signature? The answer may reach close to the Milky Way's own outskirts. Mapping this region is difficult because we observe Andromeda from inside another galaxies. The Milky Way has its own interstellar gas and circumgalactic medium. Their absorption features can appear along the same sight lines as Andromeda's. Astronomers must separate material by velocity, ionization state, direction, and models of how gas is distributed around both systems. Some features are easier to assign than others. A cloud moving at a particular speed may fit Andromeda's halo. Another may belong to the Milky Way. A third may be associated with a smaller galaxy or with gas moving through the local group. The closer the two outer environments come to one another, the less natural a sharp division becomes. The measurement also depends on which atoms are being traced. Cooler gas reveals itself through one set of absorption lines. Warmer ionized material appears through another. Very hot plasma can require ultraviolet or X-ray observations. A survey sensitive to one temperature range may find a different apparent boundary from a survey sensitive to another. The gaseous halo is not one substance at one temperature. It contains phases. Some regions are relatively cool and clumpy. Others are warm and highly ionized. The hottest material may be spread widely and detected only indirectly. Clouds can condense within more diffuse surroundings. Material expelled from the disk can mix with gas that arrived from elsewhere. The halo is an environment, not a uniform shell. Magnetic fields likely pass through it as well. Charged particles respond to those fields, and energetic processes in the disk can carry magnetic structure outward. The strength and arrangement are difficult to measure at Andromeda's distance, but galaxies are not expected to end magnetically at the last visible star. Cosmic rays may also move through the region. These high-energy particles are produced by energetic events and can travel far from their sources. They contribute pressure, interact with magnetic fields, and may influence how gas moves between the disk and halo. The full circumgalactic system is therefore more complex than a cloud of thin plasma. It is a meeting place for gravity, radiation, magnetism, motion, and chemistry. Each process operates across distances that would contain the bright spiral many times over. From the surface of Earth, none of this changes Andromeda's appearance. The galaxy still looks like a small patch. No pale sphere surrounds it in the night sky. No visible bridge stretches toward the Milky Way. The gaseous halo is too transparent for human sight, and its brightness is overwhelmed by the nearer sky. Yet the atoms are there. Some have passed through stars. Some may one day enter them. Some are escaping. Some are falling inward. Many remain between those possibilities, suspended within a galactic circulation that takes longer than civilizations to complete. The scale can be brought back to the present through the light used to find it. A quasar sends radiation from a remote part of the universe. That light crosses intergalactic space for billions of years. Near the end of its journey, it passes through Andromeda's almost invisible outer gas. A few wavelengths are absorbed. The altered light continues to the Milky Way and enters a telescope near Earth. From those missing colors, astronomers reconstruct a structure more than 1 million light-years wide. The detector never photographs the halo itself. It reads the small changes left behind. This is one of astronomy's recurring methods. Something unseen stands between us and a source of light. The light arrives, carrying evidence of the encounter. An atmosphere around a planet can be studied this way. Gas between stars can be studied this way. The outskirts of a galaxy can be studied this way. The shadow may be only a thin line in a spectrum, but the object creating it can be larger than anything visible in the image. Andromeda's gaseous halo may contain a mass incomparable to a large fraction of the stars in the galaxy. That estimate remains uncertain because so much of the material is difficult to detect, especially at very high temperatures. Even so, the halo is not a minor decoration. It is a major component of the galaxy's ordinary matter. The stars receive attention because they shine. The circumgalactic gas may hold much of the material needed to explain how those stars formed, how future stars might form, and how matter moves through the system over time. When a galaxy is shown as a bright spiral on a black background, the image creates a natural border. The light stops. The background begins. In physical space, Andromeda continues through that background. Its gas extends outward through the apparent emptiness. Its dark matter reaches farther still. Its companions move within both, and somewhere between Andromeda and the Milky Way, the outskirts of two great galaxies may already be touching without producing any light the eye could notice. The distance remains immense. The separation remains real, but the emptiness between them has grown thin. When two galaxies are separated by millions of light years, it is natural to imagine them as independent worlds. Andromeda appears in one direction. The Milky Way surrounds us from within. Between them lies a distance so large that light needs about 2.5 million years to cross it. Yet distance does not prevent relationship. The two galaxies are moving through the same local group, responding to the combined gravity of one another, the triangulum galaxy, their satellite systems, and the dark matter spread throughout the region. They have never been entirely separate. Their shared motion has been developing since long before either galaxy reached its present form. The Milky Way and Andromeda are the two dominant members of the local group. Each contains hundreds of billions of stars, an extended stellar halo, a wide population of satellites, a circumgalactic medium, and a much larger dark matter halo. The bright disks are only their inner structures. The full systems occupy a large fraction of the space between them. This makes the coming encounter more difficult to define than a simple collision date might suggest. If the outer gas halos already overlap, then one kind of contact may have begun. If the dark matter halos extend deeply into the same region, their gravitational structures have been interacting for a very long time. The stellar disks, however, remain far apart. Different parts of the galaxies meet at different times because the galaxies do not have one single edge. The most distant material is the first to interact. Diffused dark matter responds across the widest scale. Thin gas may begin mixing or compressing in the region between the systems. Satellite orbits can be altered before the main disks approach closely. Only much later do the bright stellar structures become strongly distorted. This gradual sequence is more accurate than the image of two solid objects suddenly striking one another. Galaxies are mostly space. Even inside the bright disk of the Milky Way, stars are separated by immense distances. The Sun's nearest neighboring star system lies more than 4 light-years away. In many regions, the gaps are larger. Andromeda is built in the same way. Its stars create a continuous glow only because distance blends them together. When galaxies merge, individual stars rarely collide. The disks can pass through one another, while almost every star continues through empty space. Gravity causes the dramatic changes. As Andromeda approaches, its pull acts differently across the Milky Way. The near side feels a stronger attraction than the far side. The Milky Way produces the same uneven pull across Andromeda. These tidal forces stretch both galaxies, drawing out long tails of stars and gas, while disturbing their spiral patterns. The galaxies do not behave like rigid wheels. Their stars follow separate orbits. Their gas clouds collide and compress. Their dark matter halos pass through and around one another. Their central regions move along paths controlled by the changing distribution of mass. The encounter becomes a reorganization of orbits. For a long time, astronomers described Andromeda as approaching the Milky Way at more than 100 kilometers per second along our line of sight. That inward motion is well established. The more difficult quantity is its sideways motion across the sky. Andromeda is so distant that even a substantial sideways speed produces only a tiny apparent shift. Measuring that movement requires comparing precise positions across years and separating the galaxy's overall motion from the internal motion of its stars. Earlier measurements suggested that a close future encounter was highly likely. Newer analyses, combining improved observations and more complete models of the local group, have shown that the exact future remains less certain than the simplest versions of the story implied. The Milky Way and Andromeda may pass close enough to strongly disturb one another. They may eventually merge after one or more wide passages, but the timing, distance of closest approach, and final path depend on small uncertainties in present motion and on the gravitational influence of other galaxies. Triangulum matters, the large Magellanic Cloud matters, the mass assigned to each dark matter halo matters. A slight change in sideways velocity can lead to a very different encounter. Several billion years from now, this sensitivity is expected, predicting the future of several massive, interacting galaxies is not like extending a straight line across a map. Each galaxy changes the motion of the others. Their extended halos exchange energy and angular momentum. Satellite systems contribute additional pulls. The path evolves as the systems evolve. Many simulations still produce a major interaction between the Milky Way and Andromeda within roughly 4 to 5 billion years. Some lead to an eventual merger several billion years after the first close passage. Others allow a wider encounter or a longer delay. The uncertainty does not remove the gravitational relationship. It describes the range of ways that relationship may unfold. From Earth's present location, Andromeda appears as a small oval. Over immense spans of time, its angular size would grow as the galaxy approached. Long before the disks met, the spiral would become broad enough to dominate a dark sky. Its center would brighten. Dust lanes would become more distinct. The outer disk would spread across a large area among the stars of the Milky Way. No human observer is expected to witness that transformation. The Sun itself will change greatly over the same period. In several billion years, it will be approaching the later stages of its main sequence life. Earth's surface conditions will have been altered long before the most dramatic stages of any galactic encounter. The future sky can still be modeled as a physical exercise. It shows how apparent size changes when distance changes. The Andromeda we see now is small only because it is far away and faint. Bring the same galaxy closer, and its hidden width becomes impossible to overlook. The stellar disk alone would stretch across a substantial portion of the sky. Tidal tails could extend much farther. The distinction between the Milky Way stars and Andromeda stars would become less useful as their orbits mixed. The night sky would not become crowded with colliding suns. It would become crowded with structures. Broad arcs of stars could be drawn away from both disks. Gas clouds might compress where the galaxies pass through one another, leading to new episodes of star formation. Some stars could be moved inward. Others could be thrown onto wide orbits around the combined system. A few might be ejected into intergalactic space. The solar system's own path could change. There is no reliable way to predict its exact future orbit because tiny differences grow across billions of years. The Sun might remain in an outer part of the merged galaxy. It might move farther from the center. It might pass through a different stellar environment. A direct encounter with another star would remain unlikely. The greater change would be the rearrangement of the galactic landscape around it. The familiar Milky Way band would lose its present form. Andromeda's disk would also be transformed. After repeated passages, the two spirals could settle into a more rounded or elliptical-looking galaxy, though the final structure would depend on the amount of gas remaining and the details of the merger. The name sometimes given to this hypothetical remnant is Milkomeda. The word is convenient, but the future galaxy would not be a simple combination of two current photographs. It would contain stars from both systems, mixed across new orbits. It would include remnants of their satellites. Some gas would have formed new stars. Some would have been heated or expelled. The dark matter halos would combine into a larger distribution. The supermassive black holes at the centers of both galaxies would eventually move toward one another. Andromeda's central black hole and the black hole at the heart of the Milky Way would not meet immediately. After the galaxies began merging, each black hole would continue through the new stellar system, losing orbital energy through interactions with surrounding stars and gas. Over time, they could form a binary pair. Their orbit would shrink. A final merger could release gravitational waves through the new galaxy and far beyond it. This process would occur on timescales very different from the first encounter of the disks. The outer halos might interact first. The stellar structures might be disrupted later. The central black holes could take much longer to unite. One event contains many clocks. This is why the future encounter helps clarify Andromeda's hidden size. There is no single moment when the whole galaxy reaches the Milky Way. Its components arrive according to their scale. The outermost gravitational influence has always been present. The diffuse gas may already extend into the shared region. The satellites feel the evolving local group. The stellar halo will be disturbed before the bright spiral is transformed. The disk is one of the last major structures to enter the deepest stage of interaction. What people commonly call the collision is therefore the most visible part of a process that begins much farther out. It is similar to the way Andromeda is observed today. The visible part receives the name of the whole. A bright spiral stands in for a million light-year environment. A future crossing of stellar disks stands in for billions of years of gravitational change. The language is useful, but the physical system is wider and slower. The local group itself may become more tightly bound as cosmic expansion carries more distant galaxy groups away. On small enough scales, gravity can overcome the overall expansion of the universe. The Milky Way, Andromeda, Triangulum, and many of their companions belong to such a bound region. They are not being pulled apart by cosmic expansion in the way very distant galaxies are. Their mutual gravity continues to shape their future. Beyond the local group, other galaxies recede as space expands between large-scale structures. Given enough time, many remote galaxies will become more difficult to observe. Their light will be stretched to longer wavelengths. Their apparent recession will continue, but the major galaxies of the local group will remain connected. Their futures are local rather than independent. Andromeda's approach is one part of that shared destiny. Its present distance is large by any human measure. It is small enough, however, for gravity to matter across the age of the universe. The faint light in the sky comes from a neighbor close enough to change our galaxy and to be changed by it. This gives Andromeda a second kind of apparent size. There is the angle it occupies in the sky now. There is also the region of the future it occupies through gravity. A galaxy's influence can be measured in what it will eventually alter. By that measure, Andromeda already reaches the Milky Way. Its pull contributes to the motion of our galaxy through the local group. Its mass affects models of satellite orbits. Its future path helps determine the long-term structure of our galactic environment. The relationship is active even while the stars remain separated by millions of light years. The galaxies are not waiting in isolation for a collision to begin. They are already falling through the same gravitational landscape. Their halos are responding. Their companions are moving. Their gas occupies the intervening space. Their central disks carry the visible evidence of systems whose outer regions have never been fully detached. From the ground, none of this motion can be seen during a lifetime. Andromeda holds its position among the constellations. Its approach is hidden by scale, just as its halo is hidden by faintness. A change that will reshape galaxies appears to us as stillness. That stillness is not an absence of motion. It is motion spread across too much time. The same is true within Andromeda. Stars orbit at hundreds of kilometers per second, yet the spiral appears fixed. Satellites cross enormous distances, yet remain near the same region of the sky for generations. Gas circulates through the halo, while no visible boundary changes. The galaxy is active everywhere and hurried nowhere. Its future with the Milky Way belongs to that rhythm. The encounter is not one dramatic instant placed billions of years ahead. It is a long exchange of gravity, beginning in the faintest outskirts and moving inward through structures of increasing density. First, influence, then distortion, then mixing, and only much later a new galactic form. By the time that form settles, the original question may no longer have the same answer. How large is Andromeda? Today it can be described by a disk, a stellar halo, a gaseous envelope, a satellite system, and a dark matter halo. After a merger, those boundaries will be redrawn. Some material now called Andromeda will belong to the combined galaxy. Some may be thrown far beyond it. Some satellites may survive, others may be absorbed. The galaxy's identity will change while its matter continues. Galaxies are not permanent containers. They are arrangements that gravity maintains for a time. Their stars remain real, their histories remain traceable, but their edges, names, and structures can be transformed. Andromeda itself was built through earlier mergers. Its future encounter with the Milky Way would continue the same process on a larger scale. The galaxy that once consumed smaller companions may eventually lose its separate spiral form inside a greater system. Nothing about that future makes its present structure less meaningful. A coastline remains real, even though tides and erosion will change it. A galaxy remains a galaxy, even though gravity is always preparing another arrangement. Tonight, Andromeda is still distinct. Its disk turns within its own halo, Its stars follow paths centered on its own mass. Its companions remain gathered around it. Its central light continues, crossing the distance to Earth. But the hidden size of Andromeda reaches beyond what it is now. Through gravity, it extends into what the local group will become. At the edge of Andromeda, there is no border to cross. There is no final star suspended beside a line of empty space. No last cloud of gas marking where the galaxy ends. No outer wall around the dark matter that holds its distant companions in motion. Instead, every part becomes thinner. The disk fades into scattered stars. The scattered stars fade into streams and clusters. The stellar halo gives way to diffuse gas. The gas becomes harder to distinguish from the material of the local group. The dark matter thins until its gravitation influence can no longer be separated cleanly from the influence of neighboring galaxies. Andromeda does not stop. It blends. This makes the simplest question about its size unexpectedly difficult. The answer depends on what we decide to include. Measured by the bright region visible to human eyes, Andromeda is a modest oval in the northern sky. Measured by its luminous disk, it's stretched across more than 200,000 light-years. Measured by its outer stars and tidal remains, it reaches several 100,000 light-years from the center. Measured by its circumgalactic gas, its influence may extend more than 1,000,000 light-years in some directions. Measured by its dark matter, halo, and gravitational relationships, the galaxy occupies an even wider domain whose boundaries remain partly defined by models rather than direct sight. Each measurement is valid within its purpose. None describes the whole system alone. A galaxy is not like a stone that can be placed on a table and measured from one side to the other. It is a distribution of matter, motion, history, and influence. Some of its parts shine, some absorb light, some reveal themselves by changing the paths of other objects. Some are known only through the faint chemical marks they leave in radiation coming from far behind them. The bright spiral is therefore not a misleading image. It is the most visible layer of a much larger reality. From Earth, that layer seems almost small enough to cover with a fingertip held toward the sky. Yet the fingertip hides only an angle, not a physical object. Behind that narrow angle lies a structure so broad that light requires hundreds of thousands of years to cross the familiar disk. Beyond it, the galaxy continues. The human mind tends to treat visible form as complete form. A mountain ends where its slope meets the plain. A lake ends at its shoreline. A building ends at its walls. Andromeda offers no equivalent surface. Its boundaries depend on density, brightness, temperature, motion, and gravity. Change the method of observation, and the apparent edge moves. The galaxy has always been this large, only the measurement has widened. For early observers, Andromeda was a small cloud among the stars. Later instruments revealed a brighter central body. Photography uncovered the elongated disk and dark lanes. Distance measurements transformed the cloud into another galaxy. Wide surveys found faint stars beyond the spiral. Spectra exposed gas across the outer halo. Orbital motions pointed toward an invisible mass surrounding everything else. At each stage, the universe did not become larger. Human awareness did. The process continues. New telescopes will count fainter stars in Andromeda's outskirts. More precise measurements will refine the motions of satellites. Deeper ultraviolet and X-ray observations may reveal additional phases of the circumgalactic medium. Improved models will test the mass and shape of the dark halo. Some estimates will narrow, others may change. Structures now treated as separate may turn out to share a common origin. Features thought to belong to Andromeda may prove to be part of the wider, local group. Material assigned to the Milky Way may be found within a region influenced by both galaxies. The map will become more detailed without necessarily becoming simpler. That complexity is not a failure of measurement. It is a property of the object. Andromeda has been built through mergers, inflows, stellar births, stellar deaths, and long gravitational exchanges. Its present shape is one stage in a history that began before the Sun formed and will continue after the spiral pattern has changed. A clean outer edge would be unusual for such a system. The galaxy has gathered material from its surroundings. It has pulled apart smaller companions. It has sent gas outward and drawn other gas inward. Its stars have carried heavier elements into regions where no star may form for billions of years. Its gravity has connected objects separated by distances too large for any human journey. Everything about Andromeda points toward continuity rather than isolation. Even its name encourages the image of a single object, a galaxy, one thing. But the word contains a central black hole, hundreds of billions of stars, planets that remain unseen from Earth, stellar remnants, dust star magnetic fields, cosmic rays, streams from vanished companions, clusters older than the disk, satellites on uncertain orbits, hot plasma, and a dark halo whose particles have not yet been identified. These components do not share one surface. They share a gravitational history. Perhaps that is the most useful answer to the question of size. Andromeda is as large as the system of relationships that makes it Andromeda. Its disk belongs because the stars orbit within a common structure. Its halo stars belong because their motions and histories connect them to the galaxy. Its satellites belong, at least for a time, because Andromeda's gravity shapes their paths. Its gas belongs where its chemistry, velocity, and distribution reveal an association with the larger system. Its dark matter belongs because without that mass, the motions of the visible galaxy would not make sense in the same way. The boundary is not a wall, it is a weakening connection. Far enough from the center, another influence becomes stronger. The Milky Way begins to matter more. Triangulum contributes its pull. The local group becomes the more useful scale. Andromeda passes into a larger structure without ever reaching a final edge. The same pattern repeats throughout the universe. Planets sit inside stellar systems. Stars occupy galaxies. Galaxies gather into groups and clusters. Clusters connect along filaments. Filaments form a web surrounding immense regions with fewer galaxies. Each object can be described on its own, but none is entirely detached from what surrounds it. Scale does not only make things larger, it changes what counts as the object. A photograph of Andromeda shows a galaxy. A map of its satellites shows a system. A measurement of its outer gas shows an environment. A model of its dark matter shows part of a shared gravitational landscape. All of them are Andromeda, viewed through different questions. For now, its light continues to arrive, as it did before anyone knew what it was. The photons entering a human eye tonight began their journey when early members of the human lineage lived in a world without cities, written language, or astronomy. They crossed the space between galaxies while ice sheets advanced and retreated. Species changed, and human beings learned to record the sky. Nothing guided those photons toward Earth. They traveled along the paths available to them, passing through intergalactic space until a few reach this planet. Some enter telescopes, some fall upon soil, water, rooftops, and sleeping forests. A tiny number may pass through a window and meet the eye of someone who knows where to look. The experience lasts only a moment. The light behind it has been traveling for millions of years. The full galaxy remains hidden during that moment. The eye receives the central glow, not the distant halo. It does not detect the hot plasma surrounding the disk. It cannot see the dark matter shaping the rotation of stars. It does not separate the streams left by galaxies absorbed long ago. Yet none of those unseen layers needs to be visible for the encounter to be real. The faint patch is enough to locate the whole structure. It is a doorway made of light. Behind it lies a disk turning across hundreds of thousands of years. Around that disk, old stars follow the remains of lost systems. Farther out, atoms move through a nearly transparent reservoir. Beyond them, unseen mass gives shape to paths extending across the local group. Andromeda's apparent smallness is therefore not a contradiction. It is a lesson in distance. An enormous structure can become a faint mark when viewed from far enough away. A long history can arrive in a fraction of a second. A galaxy can occupy a large part of its local universe while appearing no brighter than a trace on the night. The hidden does not need to be held as one number. It can be understood as a series of widening circles, each less visible than the one before. First the central glow, then the stellar disk, then the disrupted outskirts, then the gaseous halo, then the dark matter, then the neighboring galaxies whose motions are tied to it. At the widest scale, even the circles fail. The shapes overlap. The Milky Way and Andromeda occupy the same evolving region, their outer material spread through a space that belongs fully to neither and partly to both. Billions of years from now, their separate forms may be reorganized into one larger galaxy. The matter will remain, the boundaries will change. Stars now called Andromedan may travel through regions once belonging to the Milky Way. Stars from our galaxy may enter orbits centered far from their present paths. Satellites may be absorbed, scattered, or carried into the combined halo. The future will not erase the two galaxies. It will preserve them in altered motion. Their histories will continue inside a new arrangement. For tonight, however, the distance remains. Andromeda holds its place beyond the stars of the Milky Way. Its disk turns beyond unaided sight. Its companions travel through the outer halo. Its gas rests between arrival and departure. Its dark matter follows paths no telescope can photograph. And here on Earth, the galaxy can remain what it first appeared to be, a pale mark under a dark sky. There is no need to imagine every star within it, no need to hold its full diameter or calculate the volume of its halo. The scale can be allowed to remain larger than thought. That may be the most accurate way to leave Andromeda. Not as a number completed, but as a presence whose visible center is only the beginning. Its light reaches us first. Its true extent follows far beyond. Andromeda keeps widening after the image is gone.